Okay, so we're going to get started. So, hi everyone, my name is Marcus and this is Miro. And we are not representing our companies today. This is very much like things we do for fun, so just so you know. And we're going to be talking about robots and Java and how you can quickly get going building robotic stuff with Java using something called Robo4j, which is an easy-to-use framework for quickly getting started writing Java for custom hardware. It is a pure Java framework, so there are no dependencies on other stuff, and you can use as little or as much of it as you want to. So if you are just interested in having Java abstractions for common hardware, then you can just use that part without buying into anything else. So this is all open source, and funnily enough, we won Duke's Choice Award this year, so that was great. So this is typically what a robot would look like. You would have the hardware-dependent parts. In this case, we support Raspberry Pi and Lego today, and then we have the core abstractions of the framework in Robo4j Core. And then we have units which bring together these core parts and the hardware abstractions. And then you have your robot sitting on top. And if you want to, you can use the HTTP module to be able to communicate with your robot over HTTP. So everything called Robo4j-HW for hardware is containing these very simple to use Java abstractions for common hardware. And these you can use without having any dependency on anything else. So here's an example. If you have, so Adafruit is a very common, popular place for people to buy hardware from. And they have an LCD, and this is how you would instantiate the LCD and change the background color of it to teal, and then set the text. In this case, it has 2 lines, so it would say "Hello World" and Robo4j. So I should mention that this talk is actually a boiled-down version of a full-size, full-time Java 1 talk. So we'll see how this goes. I might be starting talking faster at some point. Anyways, so this is the way you would use the system. You would have a robo context, which is basically your robot. It contains all the little robo units that you have defined. And these robo units would be sending messages to each other over robo references. And you can use annotations to select how these are being sent, these messages. And this is all plain old Java. Then we have the hardware-specific units. And these are prepackaged configurable units that you can use on the higher level of the framework. So there is going to be an Adafruit unit that you can send messages to, for example. So you typically configure these using XML, but you can programmatically configure them as well. Threading-wise, the robo unit can decide how it wants messages sent to it. So you have a system scheduler that is normally used for sending messages if you haven't said anything else. Then there's a work one if you feel that your unit is going to do a lot of processing. Then there is a blocked one if you feel that you're going to do blocking I/O or anything else that is going to hold your thread. So typically in the Raspberry Pi case, there's going to be this number of threads in each pool by default. So your typical project is you add the units for the hardware that you have in your configuration, and then you add your own units for doing the controlling behavior. You add a class with the main method where you initialize all of this in a robo builder, and then you run the main method, and that's it. So here's a full example. We have a little LCD example, and this one contains a declaration in robo4j.xml with 3 units. We'll talk about those in a bit. Then we build this context, we start it, we get a reference to the LCD just to send the first initial message for it to show. And then we wait for pressing enter so that we can easily just shut this down over the command line if we want to. So this is the XML. And at the top there, you can see that we have this LCD unit. And from the package declaration here, we can see that that is a pre-packaged thing from Robo4j, nothing that we've done anything with. We just configured it. Same thing with the buttons. If you use the Adafruit LCD shield, you would know that it has the LCD and buttons built into the same shield. And in Robo4j, those are 2 separately configured units so that you can use them independently. And then we have the controller, which basically says, what we want to do, and in this case, we want to run demos. So the controller just takes a message, looks to see if there is a demo running. If there isn't any demo running, we will process the message, and otherwise we will ignore it because we don't want to interrupt the running demo. That would be bad. And then some initialization, we can skip that. And then the actual message processing, what we do here is if somebody presses down, move to the next demo. If we press up, move to the previous demo, select, run a demo. If there's a button that we don't recognize, we just say that on the display. So I have a demo. This is the simplest demo you could possibly do. Yet at Java 1, this was the one people applauded to the most because, hey, LCDs.
Yeah.
So,
changing the colors.
Colors. So you can't see the text here, but I'm going to change the backlight. You might see that. Colors. So yeah, this is like the smallest demo we could come up with. So Java controlling hardware. So let's see. Now Miro will talk about HTTP communication.
So it's a lot of fun to working with hardware, especially when it's failing. But it's also more fun. We've been thinking, what about to talk to the unit directly? So we developed the HTTP socket module for this, and what it does, when you simply add to your Rebel4j context the HTTP server unit and HTTP client, you allow your Rebel4 system to talk outside and receiving the messages. So as a marker did mention that we are using a strong title language, so you need to define the codecs that your message will be from the bytestream properly translated and sent into our internal bus and processed. So for making this simple, we created 3 types of annotation. The first one is a HTTP producer, which slightly enforces you to implement encoding and decoding part at the same time. If you would like to split and let the Rebel4j system knows where those classes is, you can use the REST2 annotation to implement the HTTP decoder and encoder. So Rebel4j will understand and then talk to the outside world by REST style and receiving a JSON type of messages. Simply adding the HTTP server unit inside of your context and initiating it, you will get the Rebel4j system capable to answer your GET requests. With this GET request, you get all information which kind of unit you decided to plug into your system and which kind of state they are in. If you would like to talk to any of your units, you properly configure, you use the URI/unit/unit ID. This unit ID is completely unique for the Rebel4j context. So that means you cannot have the 3, 4, just the 1 unit ID. Because otherwise the Rebel4j will not understand what you want from him. How it looks. Here is a simple Rebel4j system initiated, and you are requesting on a port what kind of units they do have. So he had 2 units. There is a small joke, the HTTP server is stopped. That means that such kind of response cannot be even processed. But it's a presentation, right? So it's not real, but it cannot happen. There is one more thing. It's a UID you get with your request in a header, and this is completely unique inside of our network. But we will maybe touch it later, but here's no time for this. Here, how it looks, the communication with your units. You are simply URI accessing the controller, which is a unit ID you have in your context. And if your message is properly processed, you have the HTTP code back, 202. If you are accessing something that is not configured inside of context, you get 404. And if you are trying to do some action or whatever, but it's not even implemented, you get a 401. Then you get also more HTTP codes, but you can take a look on the code. Here is our simple image streaming demo. It's a client. Here is the Rebel4j context. Here you see it's a pre-configured unit, One is a client and one is an image controller, which is wrapping the Raspberry Pi hardware. It's configurable according to Raspberry Pi documentation, so you can simply add and start sending images. What is more interesting on this demo is that we have the server side, which is the endpoint. And this is a Java FX application, which is simply also using Robo4j and simply showing us the images, what is happening. So by this demo, we would like to show that it's very, very simple to connect the Robo4j with other technology and start to use it. Let's go back a little bit in the beginning of the Robo4j, because at the beginning we choose the Lego hardware to develop the entire framework, and Lego hardware provide us some basic standards, some good standards we can rely on, and we can move further. As Marcus said before, we have the hardware package, which can be used completely alone, which is wrapping the hardware drivers we have written, and Robo4j units, which in this case are Lego, they are providing some basic algorithms, some basic behavior you can do up to this hardware. Here is a Robo4j context for example we do have here. It's a simple one. Why it is simple, it doesn't look like this, but all what you have here, you simply add and you only configure. You're not writing any lines of code, only the controller, for example, weapon and the platform. Platform you simply add into your Robo4j context and you say which kind of motor does what. That's all. Very, very simple. And right now we can take a look on the demo we have here. Maybe you see it. I'm having right now in my hand, it's a gamepad from Logitech, which is not really common on the Raspberry Pi hardware. And I'm having a Lego, and it works with Robo4j altogether. And I haven't done anything, and Marcus is controlling this robot by using our Java FX joystick at the same time. So this is amazing. And right now, we can a little bit move to more advanced example we do have here. And I will give my word back to Marcus.
Right. So last year at Java 1, I presented an autonomous robotic vehicle called Coff-E because his laser rangefinder eyes looks a little bit like Wall-E, and he's running Java, so it's got to be named Coff-E. And he's a 3D printed thing that is using MakeBlock for the aluminum profiles. He's using things like, lots of hardware from Pololu and Adafruit, all wired together in there he is, Coff-E. So the 3D printing technology today is kind of slow, but it's very exciting because you can get exactly what you want to. And this was the first thing that I 3D printed. It takes about 20 hours to print the thing on the top left there. so it's not a speedy manufacturing thing, but you can define precisely what you want. So it's kind of cool. And here's Coff-E at Java 1 2016 running in autonomous mode on the show floor. And you can see the laser rangefinder going back and forth, collecting information. You'll notice, maybe you won't notice, it's kind of small over there, but he's going to dynamically change how much he scans, and he's going to dynamically change his speed when he starts running into trouble. And after a while there, he's actually going to understand that that's not a good place to be, so he's going to start plotting out a new way and run off. So this configuration slide is meant to be soothing, not discouraging. It's actually, if you look at the package names, if you can see the package names up there, they are all com Robo4j blah blah blah. It's just pre-configured stuff that I've added to the configuration of the robot. So this is just declaratively saying that I have one of these in here, and then the actual logic is done by things over here, like the Misho controller and scan processor. So, off-the-shelf components that are all easily configurable. to build your own Coff-E, you can go to Thingiverse. As I said, Coff-E was the first thing that I built for 3D printing. So, you know, the direction of certain components might be wrong. You might have to realign them, etc. But you know, you can print your own Coff-E if you want to. And you can also look into the repository at GitHub to find the source for Coff-E. Full disclosure, he's not fully ported to Robo4j. I haven't ported all my source there yet, but I will. Right. Then there are some exciting tools with Robo4j.
This is amazing.
So I'm going to do a little bit of a demo here. So when I designed Coff-E, I needed to design things like algorithms for feature extraction and algorithms for for finding good paths, etc. So what I did was I let Coff-E run off in a very simple just obstacle avoidance thing around in my apartment, and I captured all the sensor data using Flight Recorder, because hey, if you want to record lots of data without having timing problems, yeah, you know, Flight Recorder might work. So that's what I did. And then I developed the algorithms for feature extraction. And this little thing up in the corner is actually not a bug. That's where I have my cutting boards. That's how my kitchen looks. So it's supposed to be like that. And yeah. And then, you know, algorithms for finding good ways to move about. So that's one of the things we have. And another nice tool is...
You forgot to mention that we have the support for JFR inside.
Yeah. That's kind of
it's obvious.
This is all using Flight Recorder, recording stuff into Flight Recorder, and then visualizing them using a little plugin for Mission Control. Now, this plugin is for Mission Control 5.5,
yeah,
6.0 is out with 9, and I'll port this eventually at some point. But you know, hey. So that's, you know, if you have your own projects and you need to do something like this, I can highly recommend this. It worked very well. Saved me a lot of time. Because you can imagine what happens if you have a robot and you put in a breakpoint somewhere. You have this real-time system that is continuously feeding other parts with data. Bad things will happen. That's actually one of the fun parts with robotics. You will see your actual machines run around and interact with physical reality in various ways. And when you have bugs, that becomes very apparent. It is a lot of fun. Anyways, so here is another tool. Because, of course, you want to use magnetometers, and I really wanted to build a JavaFX app using JavaFX 3D. So here we have when you have a magnetometer, you have soft and hard iron effects that you need to compensate for. You might have an additive magnetic field that you need to compensate for, or you might have different metals in the neighborhood. You usually have. And then you need to take this, what should be a perfect sphere, and you need to find a way to map it, this ellipsoid, back to a sphere. And this is what this does. So this is just simulated data. I'll show you real data later, but unfortunately my machine here is too weak to render that prettily, so I have this simulated data for you. Anyways, so then you just take your bias vector and transform matrix and put it into Robo4j, and then you have a magnetometer that works better for you. So I'll show you what it looks like if you have the real data. It's not pretty, but it does look like the Death Star, and that's kind of cool. And that's because I had the magnetometer in a harness for one of the axes, and that's why it looks like the Death Star. Wasn't intentional, but in retrospect, it's kind of cool. Anyways, so that's real data, and it flows much smoother on my stationary computer at home. So I guess. Okay. So let me see. Here we go. Okay,
so let's wrap it up. We are apparently in a very good time, so we maybe have a time for question answer. Yeah, we never did it before. So let's wrap it up. Robo4j should be the very simple way how to access the hardware through the Java. it shouldn't stress you. So you should take a hardware you have at home and simply plug it, use our Robo4j context, build it up, and run it. And it should allows you really quickly to build something that does make a sense for you. And we just started with this. What it started is like 1.5 years ago, we started working on the Robo4j project. Apparently, Marcus is working with the hardware a little bit longer than I do, some years. And I just started working with hardware, but in a 1.5 year, we delivered on the market right now, GitHub, with something works, which is able to control the hardware, which really allows you to use the Java for such kind of purposes. You don't have to limit yourself only on hardware, so you can build up some server and units, so you can use it independently. So.
And during this time, I had baby twins, so
Yeah.
it hasn't really been full speed.
Yes. Yeah. And I'm getting a baby, so
Yeah.
it's
So you
kind
will
of
go
a lot of
from
duties.
yeah.
But we have a small robots also. But we cannot turn it
other
down.
babies. Yeah.
We can turn them down still. So we hope that it's helped someone that make you interested in IoT work, because there are a lot of sessions how to build the IoT, but there are very few sessions how to handle the hardware using a Java. So that's probably the reason why we won the prize. And please give us a feedback how you like it, that in the future it allows us, me and Marcus, to present some stuff which is not really directly related to our work, to our daily job, but it's making a lot of fun, and you can learn a lot from using the hardware, which can you then apply on your job, like putting up the servers and configuring the microservices. The Robo4j are basically representing some agents. Every unit is an agent system, which is working. So here you can reach us on our website, so robo4j.io, and we have also a Twitter account. Marcus has the Hirt, and I have the @Mirashmiko, so you can shoot us when you have questions or you need to help with your hardware, or you would like to participate on the Robo4j development. Yeah, you are all welcome. And thank you very much. Yeah, thank you. Thank you very much for being here. And right now we have a time for question and answer.
Also, we have some other demos here that
Yes.
we didn't think we would have time to show. So if you want to come up later
Yeah,
and see other demos, we can show you.
Maybe I can run the camera with the glue-on implementation.
We have some other silly demos.
Yes. Button pusher.
Okay. Any questions? So the question was, how do I know what XML values to put into these? And the answer to that is, you don't. Well, it's typed configuration. I can show you. Mm-hmm. But the actual values are defined in the units. So you need to look at the unit. But let's take some example here. Maybe the LCD example.
No, but there is also type of, you did mention it, type integer, we support string, double, float, and then we try to write a Java doc. So
under the config element is what will get to the unit, and you will need to check the unit documentation to see what things you can configure on it. Okay, any other questions? Yeah. Yes.
Yes.
No. Well, depends. Okay, so the thing is, so the question was, you have support for Raspberry Pi and Legos, but what about Arduino platforms? And first of all, the Arduino platform has very, very little memory, precious little memory. I wouldn't be able to fit one laser scan in an Arduino usually. Depends on which one, but. Okay, yeah, so no, but you could probably, if you have things connected to the Arduino over I2C, you might be able to glean things from the implementation code for those hardware abstractions, maybe.
No, I'm experienced. I have an Arduino at home, so I use Robo4j, and I'm communicating with Arduino using Pi4j. So this is when I would like to check some motor. Then I have a C code, and I have a mood to write a program in C code. So I do this.
So one thing about programming with Java for using Java to develop for hardware is that whenever you want to emit time-sensitive things like PWM signals, for example, you're usually better off trying to offload that to a chip that is dedicated for that. So there are good chips that have built-in timers and are dedicated for emitting PWM signals, and that's usually how you do it. That said, I am using an Arduino Nano for parsing or getting PWM signals into my Robo4j environment. So sometimes, just in one case so far, I've had to sort of build something special outside of my environment and have a little bit of C code to do whatever I need to do. In this case, decode PWM signals. Mm-hmm. But yeah, it works better than you'd think to do things like scanning. I mean, you have a garbage collected language running, a garbage collected runtime that runs on a preemptive operating system, and you have all the timing sensitive stuff all over the place, and it still works fairly well. And I think that is kind of cool, right?
Next question. Yes, go ahead.
You mentioned, first of all, awesome project, so good job.
Thank you.
Thank you.
And you mentioned it was like a pure Java solution, but since you're interfacing with hardware, it also has always have
right.
interactions.
Yes.
Right.
How does this deal with that? Do you have a specific module?
Yeah.
Yes.
Right. So the question was, since you said you have a pure Java solution, and you need to interface with hardware. So how does that work? And of course, it works by us having to have abstractions, Java abstractions. So we are relying on hardware libraries on the different platforms. So in the case of Raspberry Pi, we're using Pi4j to interface with the hardware, and we have support for various kinds of hardware. Some of them can be controlled over select GPIO channels. So in the Raspberry Pi, for example, there is hardware PWM for 2 GPIO pins, I think, and so there is going to be support for that in the hardware abstractions. There is going to be support for different I2C common I2C components. So that's where our abstractions are, and there is a thin layer against the hardware for doing communication of GPIO, I2C, accessing the serial, etc. USB, yes. But if you want to do things on that level, you can do that directly using Pi4j. If you just want to have access to the USB port. But if you want to have access to, say, the serial port, and you don't want to necessarily write the decoding of the GPS information, and just want a nice Java interface for accessing the GPS, just plug it. That's when this comes handy.
Okay. So here is, for example, how the camera works. I don't know. You cannot see.
It's kind of dark.
Oh, it's dark. So if there is a light, there is a fully standalone application running with hardware and using the RPI. Yeah, it somehow works. Yeah, it is. So you can use and play with the common hardware. You can connect to Raspberry Pi and it will work. So using.
Okay.
Yeah.
So we're running out of time now. So it was a good thing that we were so fast. Yeah. And we had the opportunity to answer a few questions. Cool. Thank you.
Thank you very much.